Welcome back. This is the end of our 10.3 notes, so we'll call these 10.3b. So this starts really with your 10.38 notes. So this example problem is in your 10.3 notes, I think on the third page. So we're going to take everything we've talked about and we're going to put it together in graphing a few functions. And we'll start with f of x. So if I want to graph these functions, I'm going to look for a few features. Right? Let's start by looking for an x-intercept. And our x-intercept is going to be where 25 over x plus 2 times x minus 3 squared equals 0. And we know a fraction equals 0 whenever the numerator equals 0. Our numerator is the constant 25, which never equals 0. So that means we have no x-intercepts. Okay. Now we're going to look for our y-intercepts. And we know our y-intercepts happen when we plug 0 in for x. So that would give us 25 over 0 plus 2 times 0 minus 3 squared, which is 25 over 2 times negative 3 squared. So that's 2 times 9, which gives us 25 over 18. The next thing we can do is we can look for any horizontal asymptotes. So our horizontal asymptotes are found by finding the limit as x goes to positive or negative infinity of our function, which is 25 over x plus 2 times x minus 3 squared. And we know that we're looking for the end behavior, and so that limit as x goes to positive or negative infinity will be the limit as x goes to positive or negative infinity of our end behavior model, which is built from the leading term on the top, and since we only have one term, 25 on the top, excuse me, we take that, and then from the bottom we take the leading terms of our factors. So we're going to take this x, and then from our next factor we're going to take x, but we're going to square it. So we're going to take x squared, which gives us our limit as x goes to positive or negative infinity. And remember, we're looking for a power function here. So that would be of the form k. Our coefficient is 25 times x. And when we multiply x times x squared, we get x to the third. But when we bring it up, we have x to the negative third. We want to look at the graph of that power function. And we know that when we have x to a negative exponent, our graph looks like this. We have a positive k, so nothing flips. And from that graph, we can see that our limit to both ends, right, our limit on the left end is 0 and our limit on the right end is 0. So our limit is 0, and when our limit is a constant, we know that we have a horizontal asymptote where y equals that number. So we have a horizontal asymptote at y equals 0. We next want to look at our vertical asymptotes. So our vertical asymptotes happen where our function, which is 25 over x plus 2 times x minus 3 squared, doesn't exist, which happens when the denominator, which is x plus 2 times x minus 3 squared, doesn't exist or equals 0, which happens here when x is negative 2 and when x is 3. With our vertical asymptotes, we're going to build a little table. We did this earlier with your notes, but let's go ahead and redo it. So we're going to look at x and f of x and how it behaves on either side of our vertical asymptotes. So we need to pick a number on either side of negative 2, and then we're going to pick a number for x on either side of 3. So the numbers we pick want to be a little to the left and a little to the right, so we're going to go a tenth, so that would be to negative 2.1 to the left, and then a tenth to the right, so that would be at negative 1.9. And then we'll go a tenth to the left of 3, so that would be 2.9, and then 1/10 to the right of 3, so that would be at 3.1. And we want to take those values for x and we want to plug them into our function. So we're going to take negative 2.1 and we're going to plug that in. So I'm not going to do this out for each one, but we would take 25 over negative 2.1 plus 2, and then we would put negative 2.1 minus 3, and we would square that. What we really care about is whether our value is positive or negative. We know where there's a vertical asymptote, the limit will be positive or negative infinity. We're just trying to figure out which, positive or negative. So when I plug in negative 2.1, my 25 is positive. On the bottom, negative 2.1 plus 2 is negative. And then here, negative 2.1 minus 3 is negative. But whether it's positive or negative, I'm going to square it, which means my result will always be positive. Right? Taking a positive, dividing it by a negative and a positive will give me negative. And what that tells me is that my limit of my function as x approaches negative 2 from the left of negative 2 is negative infinity. When I plug in negative 1.9, right, my top 25 is still positive. Negative 1.9, right, so we're changing this now to negative 1.9. So negative 1.9 plus 2 is positive. And when we square, we always have positive, so this is positive. And my limit as x approaches negative 2 from the right is positive infinity. When I plug in 2.9, so these will now be 2.9, I have positive over 2.9 plus 2 is positive, times anything squared is positive, which is positive infinity. So my limit as x approaches 3 from the left is positive infinity. And then when I plug in 3.1, I get positive over positive times positive, which again is positive. So my limit of my function as x approaches 3 from the right will be positive infinity. Okay, so we're going to take all that and we're going to pull it together and we're going to draw our graph. So I'm going to sketch this off to the side. So I'm going to do an x and a y axis, and I'm going to plot what I know. I know that there are no x-intercepts. I know that I have a y-intercept at 25/18. So I'll make this 1, I'll make this 2, and I have a y-intercept at, so somewhere between 25/18, a little more than 1, a little less than 2, so we'll put that mark there. That's going to be my y-intercept. We know that we have a horizontal asymptote at y equals 0, so I'll have a horizontal asymptote along the x-axis. And we know from the graph of the power function that was our end behavior model, so we know from this that our graph is going to approach our horizontal asymptote from the below on the left and from above on the right. So when I come in here to graph, it's going to do the same thing. So we know that it's going to come from below on the left and from above on the right. So I know how that's going to end. Okay, the other thing I have is I have vertical asymptotes at negative 2. So we'll put a negative 2 there. And at positive 3. So we'll put 3 here. So we've got vertical asymptotes here and here. And we know because to the left of negative 2, we're going to negative infinity, our graph will go down. To the right of negative 2, we're going to positive infinity. So on the right of negative 2, we will go up. On the left of negative 2, we're going to positive infinity, so we're going to go up. And on the right of 3, we're going to positive infinity, so we'll go up on the right. So those are our pieces. We're going to put those together, and I'm going to sketch a graph. So we're going to go from below and then down. Here we're going to go from going up to going up, and then here we're going from up to across. And so with really pretty quick work, nothing too difficult, I get a pretty decent graph of that function. I think if you were to enter that function into your calculator and graph it, you would see that we're pretty right on here. So that's one example of using the features to graph a rational function. Let's do another one. So here I have h of x equals x squared plus x minus 2. And we're going to take this function, and the first thing we're going to do is we're going to factor it. So this is going to be x plus 2 times x minus 1 over x minus 1. And one thing we should notice here is that we have a common factor. And where that happens, that common factor produces a whole. So I know that I'm going to have a whole when that factor equals 0. So that's going to be when x equals 1. And that's going to give me something useful. So from here, I'm going to write that my reduced form of h is what's left when I divide out the x minus 1, which is x plus 2. So let's walk through our features. So we have an x-intercept. Okay. That x-intercept again is when h of x equals 0, which is when the numerator equals 0. So that's when x plus 2 times x minus 1 equals 0, which is when x equals negative 2 or 1. But the denominator doesn't. And we have to throw 1 out because 1 would make our denominator equal to 0. So we have one x-intercept, negative 2. We find our y-intercepts by finding h of 0, and that gives us 0 plus 2 times 0 minus 1 over 0 minus 1, which is, right, 2 times negative 1 divided by negative 1, which is 2. So we have a y-intercept of 2. That's our y-intercept. We look for horizontal asymptotes by finding the limit as x goes to positive or negative infinity of our end behavior model, which is going to be x squared over x, which is the limit as x goes to positive or negative infinity of x. And if we think about that graph, right, the graph of y equals x goes like this, which tells me that my graph is going down on the left and up on the right. So which means I have no horizontal asymptote. And that limit was not a number. For vertical asymptotes, my vertical asymptotes happen when my denominator equals 0. So that would be when x minus 1 equals 0, which is when x is 1. But when the numerator doesn't, and because 1 would make my numerator equal to 0, right, I have to eliminate this, which means there is no vertical asymptote. Okay, but we do have a whole, right, and what we saw about the whole is that the y-coordinate of the whole, right, so we have an x-coordinate at x equals 1, the y-coordinate of the whole will equal what we get from our reduced form when we plug in our x-coordinate, which in this case is not 0, right? In this case that is, putting the reduced form of 1. So if we plug 1 into the reduced form, we get 1 plus 2, which is 3, which means we have a whole, right? So we have a whole at the point 1, 3. So we're going to graph this. So we've got our x and our y-axis. We have an x-intercept at negative 2. We have a y-intercept at 2. We have no horizontal asymptote, but we end going down. Right? We know we end going down on the left and up on the right. And we know we have no vertical asymptote, but we have a hole at the point 1, 3. So if I come in and I put 1, 3, we know that we have a hole at the point 1, 3. The other thing that we said, we went over this yesterday, is that when we graph, apart from the hole, our graph will graph, right, according to the reduced function. Well, y equals x plus 2 is a line with a y-intercept of 2 and a slope of 1. So if I draw a line, right, skipping my hole, right, my graph of h of x looks like this line, but it has a hole in it, and that fits everything. Okay, the last thing that we'll pick up here is this idea of a slant asymptote. And a slant asymptote happens, right? So horizontal asymptotes are horizontal lines, vertical asymptotes are vertical lines, slant asymptotes are slanted lines. And those happen when the degree of the numerator is 1 more than the degree of the denominator. So if we look at this example function, the degree of our numerator, right, so our numerator is of degree 2, and our denominator, right, that x has a power of 1, is of degree 1. Since 2 is 1 more than 1, what this tells me is that we're going to have a slant asymptote. And the way we get that slant asymptote is by doing long division, dividing the numerator into the denominator. So let's, right, been a while since you've done this, let's look at this. So I'm going to do long division. I'm going to divide the denominator, goes on the outside, and it's going to divide into the numerator, which is x squared. When we do division, if we're missing a term, we add 0 as the coefficient of that term, so x squared plus 0x minus 9. Now we're going to go through a process of divide, multiply, subtract, and then bring down. So I'm going to take x squared divided by x. That goes in x times. Now we're going to multiply, and we're going to distribute the multiplication here. So x times x is x squared, and x times positive 2 is plus 2x. Now we're going to come in here and we're going to subtract. So I need to subtract each term from the term above it, which gives me 0, and then minus 2x. And then we're going to come in and we're going to bring down the next term. So I'm going to bring down minus 9. Okay, now we're going to repeat. So I'm going to come in here, and I'm going to divide negative 2x by x, which gives me minus 2. I'm going to multiply that by each of those terms. So negative 2 times x is negative 2x. Negative 2 times positive 2 is negative 4. And now I'm going to come in here and I'm going to subtract. So subtracting a negative changes it to positive. Subtracting this negative changes it to positive. And then I combine those terms, and this gives me 0. Negative 9 and positive 4 gives me negative 5. Okay. This is my remainder, and for the slant asymptote, we can ignore this remainder. So we're going to ignore the remainder. Which means that the line that is y equals x minus 2 is my slant asymptote. So if I go to graph this equation, do this over here, the line y equals x minus 2 will have a y-intercept at negative 2, and will have a slope of 1. So that means I come in here, and I have an asymptote that is a diagonal line. Okay. If I go further and I look at some other things here, my x-intercept is going to be when my numerator, which is x squared minus 9 equals 0, which is going to happen when x equals plus or minus 3. So I know that we're going to have x-intercepts at negative 3 and at positive 3. So I know I'm going to have an x-intercept at negative 3 and one at positive 3. I want to find my y-intercept. And my y-intercept comes when I plug 0 in for x. So I get 0 squared minus 9 over 0 plus 2, which is negative 9 halves. So that's negative 4 1/2. So I have a y-intercept at -4.5. So right there. Looking for horizontal asymptotes. My horizontal asymptote is my limit as x goes to positive or negative infinity of my n behavior model, which is x squared over x, which reduces to x. And that graph, right, is y equals x, which tells me that my function is going to go down on the left and up on the right. So I know that my graph is going to end up going down on the left and up on the right. Vertical asymptotes. So vertical asymptotes happen where the denominator, which is x plus 2 equals 0, which is x equals -2. So I know that at -2, right, I'm going to have a vertical asymptote. And if I do my little mini table here for a vertical asymptote, I have -2, and I'm going to take -2.1, -1.9. Right, those are my x's. I'm going to plug those into my function, which in this case is g of x. So I get -2.1 squared. Right? 2 squared is 4, so -2.1 squared will be a little bigger than 4, but I subtract 9 and I get a negative. And then I get -2.1 plus 2, which is also negative. So that is positive infinity. So that tells me my limit of g as x approaches -2 from the left of -2 is positive infinity, which tells me that my graph will be going up on the left side of my vertical asymptote. If I plug in -1.9, I square a number a little less than 2, I get something a little smaller than 4. Minus 9 is negative. Do -1.9 plus 2, and I get a positive. Negative over positive is negative. So my limit of g of x as x approaches -2 from the right of -2 will be negative infinity, which means my graph is going to go down on the right side of my vertical asymptote. Put those together, and I end up with a graph that will do this. So on the right side, I'm starting down on the right side of my vertical asymptote. I'm coming through my y-intercept. I'm coming through my x-intercept. And on the right end, I'm going to approach my slant asymptote. On the left side of my vertical asymptote, I'm going to start high. I'm going to pass through this x-intercept. And on the left end, I'm going to approach my slant asymptote, and that is the graph of my function. We'll do another one in class tomorrow before I let you take off on your own. So make sure you've got these ideas and that you can graph a rational function.